I'm sure Hong Kong would be happy to answer any questions or address any comments that people. Yeah, go ahead.
Could you explain to me how the interaction between physics and math or mathematicians and physicists interacted? I mean, can a group will be done without math, will be done without physics? Do you have friends that are physicists? I mean, you compete, you collaborate. Where does it begin and where does it end?
From the very, very long history, you can say Newton is a physicist. So in a long history, physicists and mathematicians, they work together. As I said, those mathematical equations is coming from physical law, F equal to ma, conservation of mass, and also how the light propagates is coming from the physics. I would say right now there are some theoretical physicists, and you cannot distinguish too much with mathematicians. They are studying a lot of similar problems. But in general, I think they are a little bit different. One is they are more focused on the physics underlying this. Once you have derived something physical, then how to study the equation, how to solve it, how to understand it more quantitatively, that's what mathematicians are more good at, are better at. Okay, or more interested.
There's no Nobel Prize for math.
Oh, I guess that's due to Nobel, not due to the physics. For various reasons, maybe not for a scientific reason.
But there is something called the field method.
Yes.
In math, which is...
And also there's now a Nobel Prize.
That's right.
Which is as good as this.
Yeah.
What are your opinions as to the validity or accuracy of global climate change modeling?
That's a very, very challenging problem. I don't think even nowadays you want to predict the weather. Nobody can really tell you there's an exact model. But as far as I understand, the improvement or the modern technology using a lot of information. One is you're using more satellite photos that tell you how the cloud moves. I think that's very more accurate. And also you have some model and you have supercomputer running the simulation, but then you don't match, and then how you kind of adjust your model to your true measurement and so on and so forth. They're also using statistics to predict the weather. So for the weather, the scale is so large, and no computer can do, even we have a good model, but cannot run a very accurate simulation because it's just not enough memory to put enough resolution on the whole Earth and so on and so forth. So the best way right now is combining all the information you have, but the question is, they may complement each other, but you don't want them to be contradictory to each other. So the question, how do you assimilate all kind of information together to get a better one? I think this is still, that's a challenging problem. But you can see on the web, at least you can see the weather forecast in 10 days. But maybe for California it's good, but for some areas you definitely cannot forecast in 10 days. It changes too rapidly and so on and so forth. It's still as challenging as can be.
Other questions? Ken?
Yeah, you mentioned supercomputers a number of times. To what degree do the structure of the problem affect the structure of the computer that you need to solve it efficiently? I mean, not just more and bigger, but maybe how much memory does the supercomputer have in each node, and how are those nodes connected to other nodes? Do you guys talk to the computer scientists, and how does the interaction between the algorithms and the computer architecture go?
Okay, that's a very good point. Actually, so right now there are more and more interest, there are more and more study along that line. But basically, for example, give you just an interesting example. Nowadays we see the CPU is core. You have many cores. The question is, many times if you have a cluster of computers, how you distribute the job, how the communication between the different CPUs are more crucial than the run of each CPUs. It's much simpler and much more efficient. So the simplest thing is, that's one thing people have done quite a lot, is called vectorized calculation. So if I multiply a vector with a vector, I can easily parallelize that. The first component here just go one CPU, the other one go to the other one. But for more complicated problem, how to reduce the problem as much as possible to vectorized operation, that's need mathematics. The second thing is even for a very complicated problem that, for example, the climate control, the forecast in the whole world, you know the weather, they are affect each other, you know, they're all coupled. It's not just I run, you know, the weather in California separately, run the weather in Colorado separately, and then that's good enough. You have to communicate them. How do you communicate them? That's again, the efficient way, the correct way, that's also you need a lot of mathematical study on this. But you're right, you know, with the development of progress or advance of this technology, we also have new and new problems. For example, before Google, nobody think about this. Well, eigenvalue problem is still very important, but you know, sometimes the new technology will provide new mathematical challenges and new mathematical problem. That is a type of problem right now. How to fully utilize this multi-core component in the computers.
Yeah.
Since I noticed that you said it takes a lot of memory, but I always wondered, since hard drive space is very cheap, do you ever save the past data and use it in reference to your new data? Like if you're always doing the same skin measurements, do you use past skin measurements to make the calculation any quicker? Or
Yeah. Okay. So one is in practice. One is okay. Let me first address. You know, we need a large. You know, there are two types of memory. One is data. You just store it. But the other one is when you do computation, you need that data on the fly. So if you store in the hard drive, the communication is an issue. It takes more time than do the computation. So that's not an efficient way. So, but in reality, of course, you know, if you just want to store the data, nowadays hardware, you know, hard drive is cheap and has a large memory. But as I said, it all depends on what problem you're talking about. I can always find a larger problem you cannot store in your current hard drive. So you need more clever way of doing things rather than just, you know, you increase the speed by 2. You need 100 years, you still need 50 years. It's not very good. But if you increase your speed by, you can 10, 20 times, that's really significant.
Okay, I think that we should probably wrap up here and thank Hung Kai for a wonderful talk. And once again, I'd like to thank you all for coming. Hope you have a great day. I have 2 things to ask of you. We are trying to save whatever dollars and cents we can, so if you could just take off your name tags and leave them on the table. We'll reuse them next time if you have one of these plastic covered name tags. And the next lecture, let me just remind you about, is on March 31st, last day in March. Will be by Professor Eric Grignot from the Department of Earth System Science, and he's going to be telling us about how climate warming is impacting some of the great ice sheets. So we hope that we'll all see you back. We'll see you all back here then. Thank you very much for being here.
Yeah, that's really what